And just as a request, it would be great if the questions are verbal, meaning maybe you can unmute yourself when you ask the questions. Because if you put questions in the chat box, it will be hard for me to see during the talk. So, feel free to ask as many questions in the talk as you like.
So, shall we start?
Yes.
Okay, good. So, thanks everyone for coming. This is a special seminar. It's special in two senses. The first is the special time. The other that it is the anniversary of two of the organizers. So we're happy to have Sumit Mukherjee from Colombia, who will tell us about persistence exponent of GSPs. Thank you, Sumit.
Thank you, Ohad and Naomi, for the introduction, and also, thank you for giving me the honor of giving a talk on your anniversary. So I guess it's fitting that the talk that I'm going to give today is based on joint work with Naomi and Ohad. So, okay. So before I begin, let me just repeat sort of what I said. It's you can ask as many questions as you like, but I prefer that the questions are verbal and not in the chat box. That way, because I'm full screen and I cannot see the chat box right now, and I would like to this is sort of easier for me. Okay, and don't I don't mind if I don't finish all the slides. I'm happy if I finish 2/3 of the slides. Some of the slides are only there for backup. I mean, if I need to go there, I'll go there. But okay, so let's begin the talk. Okay, so the talk will have roughly 4 components. So in the first part, I'll roughly say what is a question and what is known about the question. In the second part, I'll mention what our results are and with some explanation. And in the third part, I will outline some of the proofs. And here I've outlined more proofs than I want to present, I guess, in the talk. And so I'm happy to skip some part of it. And then I'll conclude. Okay, so let's dive right in. So this is a question that we want to study. So you have a continuous time Gaussian stationary process, and it has continuous sample paths, and it has mean 0. The variance, I just scale it to be 1. I mean, it could be other number as well, it doesn't matter. So this is the object that we want to study. And so what is it that we want to study about this? So this is the quantity that we want to study. We want to study the probability that the process stays positive for a long time, let's say for time 0t, and I'm thinking of capital T going to infinity. So we want to study asymptotics of this quantity P of t. Okay, so first of all, I mean, it's sort of almost trivial to see that Pt will go to 0 unless your covariance function is identically 1, because if it's not identically 1, that means it's less than 1 at some gaps. You can just sample those points. They will be sort of not, I mean, the correlation would be less than 1, and if you want all of them to persist, your probability will decay. That's it. And no rates, but at this point, you just go to 0. And so we want to get rates for this. We want to study the decay rates for Pt. So that's basically the question we want to study in this talk. Okay, so what is known? And so here in brackets, I say non-negative correlations because most of what we know about this problem is for non-negative correlations. Is there a bit high? This? No, I don't know. Okay, so more is known about this when the covariance function rho is non-negative. And so in this case, one can use the celebrated Slepian's lemma, which is kind of a positive association lemma. So it says, if you have positive correlations or non-negative correlations, if you want to persist on 0 to t plus s, then you can pretend that they are independent in these 2 separate blocks, 0 to t and t to t plus s, to get a lower bound. And that's this. And then you use stationarity. You just replace t to t plus s to 0s. And this is multiplicative. And so by subadditive, the usual subadditive argument, this limit exists. And it's a number between 0 and infinity. Note that here, when I define the exponent theta rho, I take a negative sign just to make it non-negative, because exponents are typically non-negative. And so this is the convention that we'll take. Okay, so can it be infinity? Under the assumptions that I put here, no. If you have non-negative correlations, it cannot be infinity. And why is that? It's very easy to check. Well, if you again use Slepian's lemma, Slepian's lemma sort of is a very common tool, at least when you have non-negative correlations. It all, of course, I mean, the lemma is general, but it's more effective if you have non-negative correlations. So I want the process to persist on 0 to t. Good. And so now I split up into smaller blocks, 0 to 1 over k. And so how many blocks I'll have? I'll have tk many blocks. And so I get this lower bound. And so all that I need to show that this is, okay, I can take a 1 over t log. This operation we'll be doing a lot of times. 1 over t log of the probability is lower bounded by k times log of this probability, log of persistence on a very small interval, 0 to 1 over k. And so all that I need to ensure that this exponent is not infinity is to ensure that the probability that we see here is not 0. That's it. If it's not 0, then you get a finite lower bound. So this is what I say in the next slide. I want the probability that the process is positive on a small interval to be not 0, and then you have finite exponent. If not, what happens? Well, if not, then this probability has to be 0 for all k. And let's just quickly check that this cannot happen. I'm going to take a limit as k goes to infinity. This is a process with continuous sample paths. It converges almost surely to x at 0, which is a Gaussian with mean 0 variance 1. And so the probability that x0 is 0 is not 0. It's half, of course. So this cannot happen. So this shows that for every k, this is positive. So you have a finite lower bound. Can this be 0? As it turns out, it can be 0. Okay, so, and in fact, we can characterize when it's exactly 0. There are various characterizations existing in the literature, but this is the cleanest. I don't know if this clean form appears before. This is a form that we sort of write in a recent draft. But okay, so what this says is that this exponent is 0 if and only if your correlation is integrable. No decay conditions, no other conditions. That's it. So if you have non-negative correlations, I can characterize exactly when the exponent is 0. It's when this integral diverges, right? If the integral is too large, you have heavy correlations, persistence is easy, that means your exponent is 0. On the other hand, if your integral is finite, that means correlations decay fast, persistence is a bit harder, and your exponent is positive. So that's basically roughly the intuition of this result, but we have this clean result. Okay, so what more do we know about this? So this is sort of a, I guess the next question that one can ask. Well, one can ask a lot of questions, but this is the next question which we know the answer to. So you have a sequence of covariance functions rho k, and you know that it converges pointwise to rho infinity. So this basically means that the finite dimensions of your Gaussian process converge. Right? That's a very mild requirement. And we want to say, well, we know the exponents exist because things are non-negative. Do the exponents converge as well? Well, this is too mild a condition, and the answer is not always. And let me give an easy counterexample of this. So you take two correlation functions, both of them are non-negative. And here so rho int is a correlation which is integrable, rho non is a correlation which is not integrable. So maybe I should have put not, but okay, so that's so these are two correlations that I have, and I'm going to take a linear combination of them. So rho k is, most of it is rho int, and a small portion of this is rho non, sorry. But clearly this is not integrable because of this portion. There is a non-integrable portion. And so, theta of rho k is 0 because it's not integrable, and we characterize an if and only if condition. On the other hand, if you take a limit of this rho k's, you get just the integrable portion, and theta of rho int is positive. And so of course 0 doesn't converge to something positive, and you don't have continuity of exponents. But you see sort of where I cheated. Essentially, pointwise convergence is not enough. You need sort of, in some sense, the integrals to converge, because the integral sort of determines whether it's finite or not. Maybe you want the integrals to converge, and one way to guarantee this is some sort of uniform integrative condition, like some sort of decay. And here we assume a bit more. So these are result. This is a result that appeared in 2015. This was based on joint work with Amir. So this says that the exponents do converge, provided these conditions hold. The first one is the same as before. Your correlations converges pointwise to the limiting correlation. And this is essentially finite dimensional convergence. Your process finite dimensions converge. The second is sort of the uniform integrability type condition. It says your rho k, all the correlations is bounded by t to the minus alpha for some alpha greater than 1. So t to the minus alpha is integrable. So it's like a DCT type condition, right? I mean, you have some bound which is integrable, and here we choose a convenient bound. There are other bounds that I could put here, but this is clean enough and captures the right idea. So this is sort of ensures that the integrals converge as well. And we also need a bit of smoothness. So this condition, this condition says that rho k's are uniformly continuous near zero, right? I mean, so this sort of gives you tightness. This sort of tells you that if you look at the Gaussian, the kth Gaussian process, they converge in law in C01, not just finite dimensional convergence, but converges. The laws converge on C01 or C0m for any fixed m. So this is sort of gives you the tightness of the Gaussian functions. So these sort of conditions are natural, but under these conditions, we can say that the exponents converge. Okay, so this is sort of what we know about non-negative correlations. Any questions at this point that I can answer? Okay, so I'm going to move on. So what happens if you go outside the regime of non-negative correlations? And okay, so first of all, we don't even know there's an exponent, and that's sort of the state of the art. And even if the exponent exists, it can be plus infinity. So persistence can be really hard to obtain. And here we give an easy example, though at this point there are a lot of non-trivial examples known. So this is the easy example that we look at here. So consider this process, which is a linear combination of two Gaussians, z1 cos plus z2 sine, z1, z2 are IRE normal. Okay, so this is, you can compute the correlation here or the covariance here, which is cosine of t minus s, which is clearly stationary. Okay, good. Also, if you take any t, the interval t larger than 2 pi, you can actually compute the supremum or infimum exactly. It is negative square root of z1 square plus z2 square. You do the usual polar transformation and do this. But now you see the problem. Your exponent is negative log of the probability that something positive is 0, which cannot happen, and so it's infinity. And like I said, this is not the most non-trivial example, but there's a lot of non-trivial examples known at this point. But this is just an example to show that things can go wrong easily, I guess. Okay, so let's look at a more interesting example, which many people have cared about. So this is the celebrated sync process. So here the correlation function is sine t over t. So that's the correlation function. And here, of course, the correlation can take both positive and negative values. And so, okay. So in this case, it's not absolutely integrable, but of course, it's integrable in an improper sense. But it's not absolutely integrable because of 1 over t decay. And it was shown in a somewhat recent paper by Antizena et al. That the persistence of this process is bounded between two exponentials. There are some constants C1 and C2, so that for all t large enough, these bounds hold. Good, so we know that this decays exponentially. And so, okay, so we don't know constants at this point. And so one important observation about this example is, okay, so of course this is true for, so whenever there's a continuous covariance function, there is a measure, spectral measure mu, whose Fourier transform gives you this correlation function. So that's Wagner's theorem. But in this particular case, the mu is very nice. The mu, whose Fourier transform gives you this correlation function, is just half times Lebesgue measure, right? So it's a very nice measure. It's a very natural measure to study, I guess. Okay, so it's a uniform distribution on -1, 1. Good. So that's sort of the sync process. Now building on this, in a paper in 2015. So now what Naomi and Ohad did is they give sufficient conditions which are general and which say that your persistence probability is bounded between two exponentials. So a similar result, but beyond the sync process. And so the main idea again is to sort of, or maybe not again, this for the first time, I guess, is that you want to study the spectral measure instead of the correlation function. Maybe that's the more natural object to study. Okay. So these are the conditions that they put. So suppose the spectral measure satisfies the following conditions. So there are two types of conditions that we'll put throughout the talk, and these, I mean, the slight conditions may vary, but the right way to think about it is we are going to put some condition on the spectral measure near 0, and we are going to put some conditions on the spectral measure near infinity. So all these types of conditions would be like this. And I know just to compare with the correlation conditions, again, if you're looking at correlations, again we'll have to put two conditions. We'll assume something about the correlations near 0, and we'll assume something on the correlations near infinity. So sort of they're similar in spirit, I guess. Conditions near 0 for mu translate to conditions near infinity for the correlation, and vice versa. That's the way to think about it. But usually we'll always have two conditions like this. And so what's the condition that they had in their paper? It's something like this. So you have a small neighborhood of the origin where mu is essentially up to two constants, small m and capital M, looks like Lebesgue measure. So it's not exactly Lebesgue measure, but there's a small piece, where mu is dominated above and below by constant types Lebesgue measure. So basically, you can think like a small sink is sitting at the origin, and then on top of it you have some other measure, but then you need some sort of upper bound here. Okay, so this is sort of the regularity near 0. So near 0, your measure has to be comparable to Lebesgue in some sense, and this is the condition near infinity. Your spectral measure has to have finite beta moment for some beta. So under this condition, the same conclusions hold. The persistence probability is bounded between two exponentials. Good.
Sumit,
yes.
Maybe for the benefit of the audience, it's worth saying that the spectral measure is simply the inverse Fourier transform of the correlations, because
right.
Granted.
So the way to go from the spectral measure to the way that I go from spectral measure to correlation is I just take the Fourier transform of the spectral measure and I get my correlation function. So this is sort of something that will make precise in maybe I should have done this before this, but this will come up soon. So thank you for mentioning that. Okay. So what is it that we don't know at this point, or prior to I guess what we are doing right now, is if you take a general correlation function, which I don't know that it's non-negative, then I don't know that there's an exponent, and it's actually I think we don't know the exponent to any non-trivial process, meaning we know of examples where the exponent is 0, where the exponent is infinity, but we don't know of any single example where the correlation changes sign and the exponent is something in between. So including the sinc process, where we know that if there is an exponent, the exponent has to be not 0 and not infinity. And so follow-up question is, in the non-negative case, we could study the exponent in terms of its continuity properties of the exponent in terms of the correlation function. And so the natural question is, can we do something similar for general correlation functions, either in terms of the correlation or in terms of the spectral measure? And also, can we compare persistent exponents if we compare spectral measures? We have two spectral measures. We can say something about those. Can we say what happens to the exponents? Can we say one exponent is larger than the other? And just to sort of mention this point, exponent larger means persistence is harder. Persistence probability is smaller. So that's sort of the connection because of the negative sign that I put while defining the exponent. And so this is sort of the type of question that we'll try to answer in this talk. So again, let me take a brief pause and see if there are questions. And this is where we'll begin the second part of the talk. And the second part will be sort of the overview of the results with an explanation. And here I'll also formally introduce the notation, so you'll see how the mu and rho are connected.
I have a question. So you asked the process to be positive for a long time. Suppose you wanted instead to know that it's bigger than some function. I don't know which function, maybe a linear function or something else. Is that very different?
So let me make first of a weaker statement and then a stronger statement. So the weaker statement is, even though we do positive, we can of course handle any level L, but that doesn't answer your. So if you fix the L, we can handle any L. That doesn't fully answer your question. If we take a function, if the function is nice enough, we should be able to do some of this. But this is not something that we address in the paper. But the techniques are very general, and the techniques should be able to handle nice enough functions. But this is not something that we did very, very extensively. So we do.
And linear is nice. A linear function is nice.
I would think linear is nice, but this is not something I should commit to before we check carefully.
Oh, okay, sure, thanks.
But I would think linear should be nice enough, yes. So as you will see, we'll go over some of the techniques that we do, and the technique sort of splits the spectral measure and then studies how to, I mean, we do, at some point, we do have to analyze persistence of one Gaussian process condition on another, and that's exactly when we analyze questions of the sort that you ask. But whether what type of functions we can handle requires a more careful study. Other questions that I can answer at this point? Okay, so let's introduce the notations. So we'll study Gaussian process through a spectral measure. So what do I mean? So take a spectral measure mu, and what do I mean by a spectral measure? I just mean a symmetry finite measure on reals, and by scaling we can always take it to a probability measure. We don't need to, but that's what I mean by a spectral measure. And then this is how I get my correlation function. So this is the connection between the correlation function and the spectral measure. You start from the spectral measure. If you do a Fourier transform, you get your correlation function. So that's the connection between the two, and this is 1, 1. And so we could characterize it either by mu or rho, as I tried to sort of indicate in the early part of the talk. But here we are going to characterize it by mu. And so, the correlation should be denoted by rho of mu. I don't do that throughout the talk, but this is sort of the way to think about it. You fix mu and then you get rho mu. And then you take so once you have a correlation, of course, I can define a centered Gaussian process with this correlation. Good. And that's the object that we'll go to study. And we are going to denote this by x of mu. And the mu, so when we'll do some of the proof sketches, the mu will change from line to line. And so we'll indicate the change of mu. So we'll put the mu to indicate that x mu is this process controlled by spectral measure mu. Right? So we don't always have to couple them in the same space, but we do need to keep track of the changes of mu. And so we want to study the same quantity, persistence of t, which is the probability that the process tests positive on 0t. And so that's the notation. And the new part is that I put a mu here and I put a mu here. That's it. Everything else is sort of the same. Okay. So with that notation, so the first main result says that the exponents exist. And so what are the conditions? And like I tried to sort of indicate, there are two types of conditions that we'll put. The first type of condition is some condition near 0, and the second is some condition near infinity. And so let's first look at the condition near infinity. And so this says that the spectral measure mu as a finite log beta moment for some beta larger than 1. So this is exactly what it means. In future, I'll sort of refer to it as a log beta moment condition, or I will say mu is nice near infinity. Right? That's I'll not write this condition too many times, but this is what this means. It doesn't blow up too fast. Okay, and I also need some sort of niceness near 0, and this is also similar to the type of conditions that we saw before in the Feldheim paper, but slightly stronger. And so again, there's a small neighborhood of the origin on which we want the measure mu to be absolutely continuous. So we cannot, I mean, there are newer versions of this so we are working on improving this. So maybe there'll be a better version of this the next time I give a talk. But at this point, what we know for sure is that these conditions suffice, is that there's a small neighborhood around the origin where your measure is absolutely continuous. And then you can talk of the Radon-Nikodym derivative, which I'm going to denote by with respect to Lebesgue measure. Lambda will be Lebesgue measure, which I'm going to denote by mu prime. And I want this derivative to be continuous, and I want this derivative to be strictly positive, only in the small interval. Outside, it doesn't need to be absolutely continuous. Even if it is, I don't need any conditions of density, but near 0, I need more. So these are the type of conditions that we need. And then the exponents exist. So again, we see two types of conditions.
Are these conditions natural under some vague definition of natural for these kind of processes?
Yes, and I'll try to convey this in the next few slides. So the next slide is actually about the conditions. Right. So first of all, first I give the example for some reason. Okay, so I lied. So first I give some examples of measures which satisfy these conditions, and then I explain the conditions. So please bear with me for 2 more slides. So the first main example is the sync process. Here mu is half times Lebesgue measure, and mu is compactly supported. So log beta moments are finite, polynomial moments are finite, every moment is finite. So it's fine. And the second is mu is of course has a density which is constant, and so it's strictly positive in the whole interval -1, 1. So second condition holds as well. So that's it. So this implies that the sync process has an exponent. Good, but what other examples can we build from sync, or maybe can we study? Okay, I've spelled above wrong, but sorry about that. So this is one operation that we can do. So suppose mu is a spectral measure which satisfies our conditions. I mean, mu of course need not be compactly supported. We did not assume that. Then the truncated measure mu restricted to -NL also satisfies our conditions. The log beta part is of course fine. Continue to the origin, the of course does not change because you're truncating the measure. And in this case, actually, we can say something more. And if I have time, I'll try to sketch a proof of this. But I'm not sure whether I'll be able to get to that far. But we know that the exponent of this truncated measure is less than equal to the exponent of the original measure. We also know that this increases to this. This thing converges to this. So all of this we know, but we know this is strict for every L fixed. Not strict, sorry. Can be strict anyway for every L fixed. Of course, if mu itself is compactly supported, it cannot be strict. Okay. So this we also have some types of comparison. So we also can compare exponents more generally. So what is the type of operation that we are doing here? We are taking mu and we're sort of multiplying by the indicator. And so sort of in a similar spirit, the proof will, okay, so in a similar spirit, if you take a function h, which is bounded, again, these conditions can relax, but these are some nice conditions which work. So take a function h which is bounded, and it is nice near 0, and nice is just means continuous and strictly positive. So h0 is not 0. And then look at this measure. Look at nu, which is d mu is h squared. H squared, of course, makes everything positive. This does satisfy our conditions, meaning this new measure, which you get by a transformation of the old measure, also has an exponent. So your mu has an exponent. This tilting also, okay, not a tilting, but this change of measure also has an exponent. Can we compare? Well, comparing requires more conditions. There can be multiple sufficient. So you'll see the comparison techniques. Let's see if I can present the comparison proof technique. But it requires, I mean, we can do it under many conditions. One sufficient condition is that its Fourier, h hat, is non-negative. This is not the one that I use for the truncation, but this is one condition. And like I said, the proofs are flexible, and we can play around to get other types of conditions that we want. Okay, so this, you can handle these separate transformations. This is sort of an easy thing to see. If mu and nu satisfies the conditions, mu plus nu does as well. Alpha times mu does as well. And mu of, if you do a time change, mu of, this is not a time, this is sort of, okay, so you look at the law of x over alpha, basically. You do a scale change, I guess. This measure also satisfies this condition for any alpha positive. So you can build more examples like this. You can add linearly. You can also do different kinds of convolutions. You can also do convolutions. Again, here, these are some types of conditions that I put, and these can be played around with a lot. And so mu and nu, suppose they have densities with respect to Lebesgue measure, and at least one of them has a bounded density. So good. So one of the densities is in L infinity, the other is in L1, so they are conjugate spaces, and that ensures that this convolution measure mu star nu has a continuous density, and the density would be positive because mu and nu has some mass near 0. So the convolution also has an exponent. So if mu and nu are have density, nice, I guess. I mean, nice varies from line to line, of course. But if mu and nu are nice, then the convolution mu star nu is also nice. So this also has an exponent. Okay, so I started the talk with the correlation function. So let me mention a condition in terms of the correlation function. So if the correlation function rho is absolutely integrable, you don't need it to be non-negative. And so this is the condition near infinity for rho, and you have this condition for near 0. So this is sort of the log beta or equivalent of the log beta moment condition for the spectral measure. Then again our conditions hold and we have an exponent. But let me mention that this is not the optimal version in terms of correlations, and I mean the optimal version that we have is in terms of the spectral measure. The version that I state here in terms of correlation functions does not apply to the sync process, because for the sync process, as I mentioned in the early part of the talk, the correlation is not absolutely integrable. It is, of course, I mean, it's integrable in a proper sense. The integral from 0 to t has a limit. And so if I had to guess, most likely this should be the right conditions in terms of the correlation function. The improper integrals have to exist. Integral has to exist. But we don't know this at this point. So at this point, we don't know this. So this would be the guess. So any questions about the examples that I gave? So the examples are sort of trying to convey or maybe partly answer the question: are these natural conditions, by demonstrating enough examples where these conditions are met. And I think I also, the next slide should talk about the conditions explicitly. Okay, so let's look at the conditions that we pose. So the log beta moment condition I would classify as extremely mild, and the reason for this is it's sort of the bare minimum which ensures continuity of sample paths. If you have, so for example, if you have a log beta moment condition for, so you need this for beta larger than 1, and of course this, I mean, you need the sample paths to be continuous. Otherwise, I don't know how to define an infimum, or I mean, this sort of takes the question in a different direction, which we don't want to pursue. But we want to sort of ensure the sample paths are continuous, and this is sort of almost, and this is not if and only, but this is almost the right condition for continuity. There's almost no condition better known in literature for continuity of sample paths. So that's sort of the bare minimum. The main condition, so this, like I said, is sort of some sort of niceness near infinity. The main condition that we need is mu is nice near 0. That's the condition, and that's actually a needed condition, as I'll try to convince you. So this is what we need, just to remind you. So in a small neighborhood of the origin, so mu is absolutely continuous, and its density is continuous and strictly positive. And so we are trying to lessen these conditions, but it cannot be lessened too much, as this example shows. I'll not go into the proof of this example formally, but essentially, so this is the way to think about this example. So mu is a plus b cos of 1 over x on this set. So what this is doing is, this cos of 1 over x doesn't have a limit as x goes to 0. So everywhere else is continuous, but only at 0 I cannot extend it continually. And that's it for this nice, for this very nice spectral measure. The exponent theta nu does not exist. So that sort of tells you that some condition near 0 is needed, right? 0 is somewhat special, right? You can have continuity everywhere, but continuity at 0 is, sorry, you can have a discontinuity at other places, that doesn't matter, but a discontinuity at 0 is severe. So let's sort of summarize the main points about this example. So in the example, mu is of course compactly supported. It's on -1 1. It's absolutely continuous. I wrote a density, and also the density is continuous everywhere except at 0, where I cannot extend this continually. And that's it. And that tells me that there's no exponent. And so this demonstrates the special role of the origin of this problem. I mean, sort of discontinuity derived from the origin that has no impact on existence.
Sumit, in the example, could you show it again, please?
Yes.
Was there A less than B there? So
sorry, it's A greater than B. It's A greater than B. I apologize.
All right.
A greater than B, because I want this function to be positive. So you're right. It's A greater than B.
Okay, thanks.
That's a type. So I want this. So I want the spectral measure to be strictly positive everywhere because I don't want it to be messed up because of other reasons. So it's a strictly positive density. You know, by the way, we could make this example not compactly supported. That's not the main issue here, but compactly supported measure is actually nicer, which is why we wrote it this way. And so okay, so that's that. And so sort of the conjecture that we want to make about this example is the exponent should not exist for any AB, because the intuition that I said applies to any AB, but currently our proof only applies for some AB. So we carefully choose AB to make this work. But yeah, we believe that with a bit more work, one should be able to show that the exponent does not exist in this example for any AB. I mean, okay, so any AB with the restriction that one of them is larger than the other, and I forgot which one. You need it to be non-negative.
And then this is because there is one sequence that you know where it tends to one limit and another sequence where it tends to another limit. And
exactly. Yes. Yes. So that again. Sorry.
Is it on the integers that it's okay, or?
It's not on the integers, but we have two subsequences of reals.
Okay. All right. Okay. Thanks. Very good.
Okay. So that's that. Okay, so that's I guess the comments about the first theorem, or the first main result as well. So now I will introduce the second main result, which says something about continuity of exponents. And so what does this say? So I want the exponents. I have a sequence of spectral measures which is converging to a limiting spectral measure. No. This is sort of, sorry, I made some changes yesterday, which I forgot about. So the second result is not about continuity of exponents. The second result is what happens. Okay, somehow I cannot see the totals. Like, okay, what happens when we add singular measures? And this is sort of another thing that comes out of our study. And so suppose mu is nice near 0 and infinity, and nu is a spectral measure which is nice near infinity. Nu cannot be nice near 0 because nu is not nice anywhere, because nice means that you have a density and stuff. And a singular measure, of course, cannot have a density. And so we want to study what happens to the exponent of mu plus nu. And so assume further that nu is not supported near the origin. So near the origin, like I said, we need a bit more. So we don't want nu messing up things near the origin. Put it anywhere else, we don't mind. And so under these conditions, of course, mu plus nu is nice near 0 because nu has no impact near 0. And mu plus nu is nice near infinity because both of them are nice near infinity. And so both these exponents are well defined by what I said previously. Good. And so our second main result, though I think in the paper it's third anyway, our second main result is that the exponent does not change if you add a singular measure. Right? So I can add a singular measure that does not change the exponent. Okay, and so this sort of says that, while studying exponents, if you have a singular measure away from 0, just throw it out. That's it. I mean, okay, near 0, don't put a singular measure. Away from 0, throw it out, and without loss of generality, you can assume that your spectral measure has a density everywhere. So that's sort of how the proofs usually go. First throw out the spectral, first throw out the singular part, and then work on the rest of the measure. So I mean, okay, I mean, I guess I may not be able to go to the proof section, so let me just mention this could be a good point. So we first
can you explain what the importance of the fact that nu is singular is?
Yes. So if nu is singular, then essentially
it's not true for a non-singular measure, or it is true for a non-singular measure.
It may not. Okay, so for example, the way that I stated, even if I take nu equal to mu, this would be true because theta of 2 mu is theta of mu because I'm looking at persistence at 0. But if I'm looking at persistence at different level, then theta of 2 mu would be different. But what is special about, so it can be true for non-singular measures as well, depending on what level you choose. But for singular measures, this is always true. And the reason for this is singular measures can be reasonably well approximated. So think of a singular measure which is let's say, so the way this works is we first approximate singular measures by sampling. So we have a discrete singular measure. So we have a discrete time process whose spectral measure is singular. And for the discrete time process, we can approximate this singular measure by small o n many independent Gaussians, linear combinations of small o n many independent Gaussians. So essentially, even though the singular measure, so essentially, even though you're looking at persistence of n objects, you can write it as a probability on small o n many Gaussians, and that gives and sort of, if you had small o n many independent Gaussians, then the persistence probability is of course sub-exponential, and a more involved version of this argument applies. So singular measures can be well approximated by linear combinations of small o n many Gaussians, where n is the time point that you're looking at. So the n is the equivalent of t in discrete time. Does that help? So if you have a singular measure.
Sorry, can I ask a question?
Yes.
Yeah. Suppose I got a singular measure which just has a single point, it's a single atom.
Right.
So that's like just adding a sine and cosine.
Yes.
But it's got a huge mass.
Yes.
Compared to the mass of the original measure.
So it can
So
be
I'm
huge.
taking the original process,
right,
and I'm adding this big sine cosine curve to it.
Yes.
That doesn't change things?
So it doesn't, and that's actually my next example. Let me just.
Well, okay.
So this is your example, I think.
Yeah.
You put so you have to make it symmetric, of course. You have to put some mass at 1 and some mass at -1, and then you have this Z1, Z2. So okay, so here I put, of course, mass half, but remember your singular measure still needs to have a finite mass, right? So you cannot put infinite mass. No matter what finite constants you put, it doesn't change the exponent. You're right. But this requires this sort of the way to the way this proof is sort of a bit involved. But the right idea is that I can express the singular measure as small o n many Gaussians. Here are only 2. The singular part I can express as in terms of small o n many Gaussians. But this part is right. So it doesn't matter what weights you put there.
Okay.
Okay, so how am I doing with respect to time? So I have like 7 minutes. So let's so this sort of, so what I was trying to mention here is that if you cannot put the singular measure at 0, because if you put the singular measure at 0, then no matter how small weight you put, your exponent will just drop down to 0. It is very easy to persist if you have an atom at 0. So that's why 0 is special. This demonstrates again. But put your singular measure anywhere else. Put point masses, put other types of singular measure, doesn't matter, away from the origin, then you're fine, as long as your singular measure has finite mass and satisfies some log beta moment conditions. But those are mine. So that's sort of the comments on the singular measure part. So let me mention the third main result, and then I'll sort of jump to the conclusion section. So the third main result says something like this. So your exponents converge, and that's sort of the continuity result. If 1, the mu k's are uniformly nice near infinity, that's for some beta, all these log beta moments are uniformly bounded. Of course, this is a natural condition. You need 1 for everyone, but you need uniformity. And mu k's are uniformly nice near 0. That is, there's a small neighborhood which doesn't depend on k. So then mu k's are all absolutely continuous on this small interval, and the infimum of these densities are positive. This is sort of what we need near 0. This is the right or a right version of the a right extension of the condition that we proposed before. And of course, we need some sort of convergence. We need the densities with respect to Lebesgue measure. I don't care what happens to the non-singular part, whatever singular part, because okay, it doesn't matter. We need the densities with respect to Lebesgue measure to converge in L1. But so far, we haven't put enough conditions near 0. We also need the densities at 0 to converge. So that's right. So we need the densities at 0 to converge. So under these conditions, the exponents converge. So that's our third main result. And I'll in the next slide, I think I talk about the conditions. Any questions on this result? So this condition C is like an L1 condition. You can think of it as similar to the, okay, it's not of course equivalent. It's actually weaker than the L1 condition that we studied before. So this continuity theorem implies the previous continuity theorem in terms of correlation that I stated in the early part of the talk. There we did not need this extra condition because, so this is basically saying, so mu at, so the density at 0 is basically the integral of the correlation function. So this is basically saying the integrals converge, which was guaranteed by other types of conditions, the uniform integrability and pointwise convergence. So this result actually implies the previous continuity version. So this is indeed a generalization. So what are some comments? So of course we need some conditions near 0 and infinity, uniform because they're natural analogs, I guess. And the L1 convergence sort of conveniently works only on the non-singular measure. I don't care about what happens to singular part, just the non-singular. Look at the density with respect to Lebesgue measure and then look at L1 on that. Nothing is needed for the singular part because they don't impact anything. And so this result generalizes the continuity exponent that we saw in the early part of the talk. Okay. So, so this sort of ends the second part of the talk. And at this point, I would skip the outline of the proofs and go straight to the conclusion, but I'm happy to take any questions at any point. And I am happy to go back as well. Okay, so let's sort of jump a bit. Let's see, I guess it would be like maybe a bit before. Okay. So, okay. So sort of the summary of the results that we presented so far as follows. So we give a general set of tools for analyzing persistence of Gaussian stationary processes. You don't need non-negative correlations for what we do. And so we established that there is a persistence exponent for any spectral measure, any within quotes, because you need some conditions, of course, because there are counterexamples where there is no exponent. And we give examples of these kinds of counterexamples. We also study continuity of persistence exponents under appropriate distances, the distances being L1 plus convergence at 0. We also show, okay, this is the part that I, this is also an ingredient that goes into the part showing. So one of the reasons the singular measure does not change exponent is because the Ball exponent of a singular measure is 0. So what do I mean by the Ball exponent? So suppose I look at the probability that x of t is absolute value of x of t is less than delta on 0t. So instead of looking at persistence on the positive half, I look at persistence on minus delta delta or some delta fixed, and then take 1 over t log of the same thing. This exponent would be 0 if and only if mu is singular. And this is sort of what goes into the singular part as well. So this is where we use the intuition that I tried to sort of mention. The way we prove this is by approximating a singular process in discrete time by a singular process in continuous. So other way around, singular process in continuous time by singular process in discrete time, and then we express the singular process in terms of small number of Gaussians approximately. But this is sort of an important result in its own right. And so using this, we show a second main result that the persistence exponent does not change if you add a singular measure, which is not at the origin. And so what are some things that we leave open at this point? So the first exponent is, what is this? First question is, what is this exponent theta mu? Like, okay, is it some nice functional, or okay, I mean, can we express it in a, can we say what this answer limit is? And I don't think we are close to answering this question. And I'm not, this is sort of making an assumption here, but I think nobody knows. But yeah, I may be wrong on this. But if for specific examples, yes, but for most non-trivial examples, we have no idea what this exponent is. And also in this talk, we only studied exponents where spectral measures have finite positive density near 0, which is the nice near 0 part. And so one can ask what happens if your density blows up near 0 or dies down, goes to 0 near 0. And so, okay, we know something about these kinds of examples. We know upper and lower bounds on the log persistence, but we don't know there's an exponent. And here, when I say exponent, I mean you take the log probability and rescale it by, not by t, but rescale it by whatever makes it non-trivial. If you divide by t, you will get 0 or infinity as answers, but you want to rescale by something other than t. And the last question is, can we handle non-stationary Gaussians? So the reason why this spectral approach is very nice for stationary Gaussians is because, if you have a correlation function for stationary Gaussians, it can be written as a 1-1. It can be written, it is a 1-1 correspondence with a spectral measure, and it's unclear, at least to me, what is the right analog for non-stationary Gaussians. If you have non-stationary correlation, what is the right analog for spectral measure? So one advantage of looking at correlation functions is that, that makes sense even for non-stationary Gaussian processes. But so that's something which one should try, or maybe we should try at this stage. So with that, I think I'm at the end of the talk. I'd like to thank all of you for your patience, and I apologize for going a bit fast. And I'm happy to take any questions. Yes.
So any questions for Sumit?
Yeah.
Yes.
If I can make a question basically on this non-stationary business.
Mm-hmm.
I mean, this is sort of the answer to Evyatar's question right at the beginning, right? Can you do this for, say, a linear crossing rather than a straight line? Okay, and I think the answer is no.
Okay.
Right, because you have stationary processes.
Right.
Like variance 1.
Right.
Look at a linear line growing
Uh-huh.
with slope 1.
Right.
Then after t units, the probability of being above that
Right.
is like e to the minus t squared.
Right.
So it's completely the wrong order.
So you're right. So I don't want to claim, so this is sort of also relates to what I said in 2. I don't want to claim that I always divide by t. In this talk I do, but in question 2, I say that you're allowed to rescale by whatever makes it non-trivial. But the techniques that we propose in this draft, or there's no draft at this point, there's no draft on the archive at this point, but the techniques that we propose does not require, all of them do not require that I rescale by t.
Okay.
So you are right. The scaling may be different. The scaling may depend on your function. Well, if your function is continuous and bounded, then of course the same scaling will apply t. If your function is growing, then you may need to rescale. You are right. But so we do know something about non-stationary processes. So the version of continuity theorem that I mentioned in the early part of the talk for non-negative correlations, this is the one with Amir. That one is actually for non-stationary processes. So that's the way I stated it. Let's see. Let's see. Maybe earlier than this. So this result I stated here for stationary correlations, but the result that appears in the paper actually is for non-stationary correlations. It looks a bit more ugly, but it applies. So the examples that we use in that paper is for random polynomials, which is non-stationary, which is only approximately stationary when you transform. So if approximately stationary things converge to stationary processes and they are non-negative correlated, we do know a lot, but they do need to be. So for approximately stationary processes, at this point, we do need them to be non-negative correlations. We cannot handle general correlations.
Stationary increment Gaussians. That would be the next thing, I guess, to look at, right?
That would be the next thing. So whenever you ask a new example, I guess my answer would be we have to think a bit more carefully. But if at any point you say if the differences have non-negative correlations, then I'm more confident. Whenever you give me non-negative correlations, usually I'm more confident about it because I can use Slepian a lot more. Right. So the theorem that I state here uses non-negative correlations in a very strong way, but it does have an analog for non-stationary processes.
Let me ask another question.
Yes.
Do you have also a rate of convergence to the exponent?
We do have some bounds on the rates of convergence to the exponents. So for example, So if your correlation decays fast enough, then we have an explicit bound depending on how the correlation decays. So in general, we don't write out all the bounds, but for this example, we do write the bound, or we do plan to write the bound explicitly. So we do have bounds if your correlation decays fast enough. In general, we can have bounds for our main results, but they will get.
But then it's is it then 1 over t, or what is it?
So if your correlation decays like 1 over t to the 1 plus alpha, where alpha
no,
is
if it decays even faster. Yeah.
So the faster decay you, so
the better, sure.
Right, the faster the better. Yes. So we assume the polynomial decay of correlation, and we got a polynomial bound on the error.
I see. Okay.
But the more transformations we do through this process, I mean, once we remove singular measures and once we do this, all of these have approximations. It sort of keeps getting harder if we want to keep track of all the errors, but potentially one can. All of our lemmas are quantitative. We are not sure whether our main theory is fully quantitative. Right.
Okay. And another question, if I may,
yes.
And this is more vague. Is there any extension to Gaussian stationary processes in 2 dimensions, higher dimensions?
So okay, so if you give me a Gaussian stationary process in 2 dimensions with nice with similar nice conditions near 0 and infinity, I believe all of so the techniques are general enough that they can be easily extended to higher dimensions. The harder question, which is, so in 2 and higher dimensions, people look at processes which may not look stationary at all, and those are the type of questions that won't be attainable by this. But this goes beyond the talk anyway. But if you give me Gaussian stationary process in high dimensions, our theory should extend very naturally, almost a repeat.
All right. Okay. Thanks.
Okay, so let's thank Sumit again.
And I should stop my screen share now?
So.